Hello everyone, am I audible?
Yep.
So I would like to thank the Lower Bounds program organizers for inviting me here for the semester, and would like to thank Shubhangi and Madhu and Amir for giving me a chance to speak in this workshop. I'll be talking about a joint work with Suryajit Chillara and Shrikant Srinivasan. So let me get started. Just so that we are on the same page, I don't think anybody needs this definition here. An arithmetic circuit is just a directed acyclic graph whose nodes consist of plus multiply gates or input gates. Output gates, input gates are the leaves, output gates are the degree 0, out degree 0 nodes. And if the underlying graph is a formula, is said to be a formula if it's a tree. The size of the arithmetic circuit is the number of gates. You could also consider wires, the regime we are working on, it's not going to matter. And the depth of the circuit is the longest input to output path. So all of us know this already. Arithmetic circuits can be easily layered so that every alternate gate is plus, multiply, etc. And a notion of depth that we will use in this talk is product depth, which is just constant factor away from the depth that we define. This is the number of product gates that you encounter from every leaf, the largest number of product gates you will encounter from a leaf to, from input to output path. So again, we are kind of familiar with all this. In this talk, I'll be focusing on multilinear restrictions. You heard about this in Rinal's talk and in Ilya's talk. Multilinear polynomials are polynomials where every variable in a monomial appears at most once. And a computational model, either circuit or formula, is said to be multilinear if every gate inside it computes a multilinear polynomial. It's slightly different as compared to syntactic multilinear, where you also assume that for the multiplication gate, two subtrees don't share variables. Here it could happen, but every node eventually computes a multilinear polynomial. And this is the running example, which is also a multilinear polynomial, very trivially. All right, so multilinear as a restriction has been studied in the past. So matrix multiplication is a topic we studied quite a lot in this workshop. This is a very natural class of polynomials that people consider which are multilinear, such as matrix multiplication, determinant, permanent. These are kind of bread and butter for most people here. I don't have to sell multilinearity in terms of polynomials. As a model of computation too, it has been well studied. It is a restriction, but we know very few things about this restriction as well, so it makes it an interesting one. There was a breakthrough result by Raz in 2004, which got many people interested in this restriction. There was a prior result by Nissan and Wigderson, which I'll talk about. So in this talk, just for the sake of consistency, I'll refer to all the authors with their last name. So it might sound a bit formal, but let me just do that. Multilinear formulas for determinant, permanent. So what Raz's paper showed was that multilinear formulas for determinant or permanent must have superpolynomial size. So this was the first non-trivial lower bound that we witnessed in the literature of lower bounds itself, in some sense, for a large class of, for a big enough class of, for a big enough model. And the kind of tools that Raz introduced in his paper have been really influential. There has been a series of results based on this main tool that was introduced by Raz, and later it has been extended by many beautiful works, such as another paper by Raz, a paper by Rash Pilka Yehudev, a paper by, some of these I will talk about in a little more detail in the next few slides. So what I just said was multilinearity is interesting for different reasons. So in this talk, I'll be talking about iterated matrix multiplication. This again is a polynomial that all of us know quite well. as a problem, it's defined as take n cross n matrices, D of them, and try to compute their multiplication. There are many variants that one can define. For instance, you could want a specific entry from this final matrix. You could want the trace of the final matrix, and all of these are more or less equivalent. In the Boolean world, this problem, if all the multiplications and additions are thought of as over Boolean semiring, then this basically encodes the reachability problem, which is quite central in the Boolean world. If multiplications and additions are done over naturals, for instance, then you capture the class sharp L. So in that sense, iterated matrix multiplication has been quite central for a while. In the arithmetic world, the variant that we will study consists of, you think of these matrices as consisting of formal variables, and now one defines a matrix over these formal variables. Every matrix rests over or has support coming from disjoint sets, and these sets are naturally mapped to the matrices. And now you are interested in, say for instance, computing the sum of the first row of the resultant matrix. I'm defining iterated matrix multiplication so because we will use it in this form, but you could have done any other thing like trace or the 1,1th entry, whatever you like. Okay. As I said, many other variants could be studied. And this also is, as a polynomial, really well studied. So probably I'll not be surveying the various works that proved various interesting things about iterated matrix multiplications, but you can look up some of these really nice surveys. So for results on matrix multiplication before 2010, the survey of Shpilka Yehudayev is excellent. And there is a survey that is being built by Saptarshi, which deals with results that came about after 2010. Alright, so we talked about matrix multiplication. So I'm going to try to prove a lower bound about matrix multiplication. But before proving lower bounds, let's try to see what kind of upper bounds we can prove for this problem. Yeah? But let me just say one more thing. As I told you, upper bounds are just by using something like Savage, you can prove a simple upper bound for iterated matrix multiplication. You build a divide and conquer like strategy. You get a log depth circuit that computes iterated matrix multiplication in polynomial size. No surprises there. However, suppose I was to compute iterated matrix multiplication by depth delta circuits. So I have this instance of iterated matrix multiplication, and I want to compute the resultant using a depth capital delta circuit. Then the following divide and conquer strategy may be more useful. Rather than cutting it in the middle like Savage, you cut it at the right places, right? So what you do is you create let's say t is something like d to the 1 by delta, and you create d by t many such paths. And now when you want to write, let's call this matrix obtained by multiplying these things as n1 and matrix obtained by multiplying these things as nt, then essentially the overall IMM is IMM of these n1 nt. And then you can write a simple recurrence which basically says that if I'm trying to multiply D matrices and I want a resultant circuit of depth delta, then in fact so what I'll do essentially, oh wow, okay. Not able to live on the edge.
Give yourself 30 more years, you'll do it.
I compute these, so I hope this recurrence is clear. Just to make this recurrence clearer, I'm writing down the expansion. Each of these is an instance over d by t matrices of IMM, and I assume that I can have a delta minus 1 circuit for this with a little more overhead. And now for the final, this plus multiply, I just put a brute force circuit of size 2 to the t. When one solves this recursion, what you will get is, you get a circuit of size n to the is it? I don't know. Yeah. So it's easy to figure out. Yeah.
The additive thing is n to the order t.
Yeah, n to the order t.
The line above.
The line above the last two.
Yeah, you're right. Thanks. Alright, so we trivially get this upper bound, and when you have a circuit of depth delta, to convert it into a formula of the same depth, you pay a little extra size in the exponent in terms of the depth delta. So this simple divide and conquer strategy gives us multilinear formulas of product depth, this much, and size, product depth delta, and size n to the order delta d to the 1 by delta. Of course, if we try to do instantiations of this, as I already said, by Savage-like strategy, you get a formula of size n to the order log d. You get a circuit of size polynomial, but formula of size n to the order log d if capital delta is log d. Another interesting thing about IMM, iterated matrix multiplication, it has strong self-reducibility properties, which then means that getting better than n to the little o of log d for any d can lead to better upper bounds for d's larger than that. So it's not like by going to a smaller d we lose the complexity of the problem. Okay. So that's the setup for IMM. And now let me just tell you what our result is about IMM. So we study multilinear formulas for very small n, basically just 2 cross 2 matrices and d of them. So we keep d as a parameter, n has become 2. So just for simplicity, let me just denote it by IMM d from now on. What we show is that for any delta smaller than log d, any product of delta multilinear formula that computes IMM must have size whatever you expect it to have by the upper bound. So it appears that delta appears in the exponent of 2. Note that IMM has polynomial size circuits and even polynomial size formulas if the size of the matrix is just 2. So in that sense, this is a very nice polynomial that has small depth, log depth formulas of polynomial size, but for any delta smaller than log, it requires more than polynomial size.
What is product
What is
depth?
product depth?
Yeah, product depth is the number of maximum number of product gates that you may encounter while going from leaf to root. It's just like depth. It's easier to do some accounting with this.
So the improvement is putting the delta,
In the exponent.
adding the delta to the d to the 1 over.
That's right, that's right. So this is the result. The result has 3 applications. So I'll just say a little bit more about this result and how it relates to the previous results about this, and then give you these 3 applications of this result. Okay. So first let's see how it relates to the previous work. Oh, before that I have to just make a small remark which is similar to the remark I made over there, which is that from formula lower bounds you can recover circuit lower bounds. Because from a circuit, by just giving a little extra blow up, you go to a formula. So naturally you cannot have circuits of very small size if you cannot have formulas of very small size. So this just comes out as a corollary of the theorem. Okay. So as I said, let's relate it to what was known before this. So there is a result of Nissan and Wigderson from 97. So a really beautiful paper, and it shows that in fact for the same polynomial, it gives a lower bound for circuits. So we recovered this lower bound, but now we can prove a tight lower bound even for formulas.
What is SIT multilinear?
Yeah, so I actually would not like to talk about it, but it's a restriction of multilinear. So they managed to show it for a slight restriction of multilinear. There was another multilinear formula lower bound that was known. So what this showed was there exists an explicit polynomial on n variables that is computable by multilinear circuits of polynomial size, but they require multilinear formulas of superpolynomial size. In fact, size n to the omega log n. Now, this result is also similar in the spirit, but except they get that the polynomial that is hard for formulas is computable by circuits, whereas the polynomial that is hard for formulas in our setting is in fact computable by formulas of little higher depth in our case and polynomial size. So it's related, but their upper bound happens to be a circuit upper bound, ours is a formula upper bound. Yet another very, very interesting result of Dwyer, Malod, Perifel and Yehudeha separates formula from ABPs in the multilinear setting. So what they say is that there exists a polynomial, explicit polynomial on n variables computable by ABPs of size poly n, but any formula computing it must have size n to the omega log n. Now one may be tempted to deduce a lower bound from ABP lower bound and IMM lower bound, because ABP kind of reduced to IMM. Unfortunately, if you stare at the reduction, it breaks the multilinearity. So you may have to substitute the same variable multiple times when you go from an ABP to an IMM instance. So as a result, you don't recover a lower bound for IMM polynomial itself. So the two results are really similar in spirit in that both of them may give a separating example. However, it's not IMM, and that it is IMM is helping us for these applications that I'll talk about in the next few slides. Yeah.
But maybe another known result that's relevant, that's in the Boolean world, the Ben-Rossmann result, which seems very analogous.
Yeah, I'm going to mention that. It's absolutely analogous, and I'm going to mention it. You're right.
Just comment from my side. So I should think of basically the simulation of ABP by IMM as a case in which being not multilinear is important. Right?
Yeah, I mean, we don't know of a reduction that preserves multilinearity.
When you say but any formula computing it, you mean any multilinear formula computing or?
Yeah.
Yeah, because I was just...
Yeah, you're right. I should have said. Yeah. They're up there, but yeah, I should say.
Yeah,
you're right. So these are the known results. So let me now tell you there are three applications. So application 1, 2 and 3, and I'm going to put it in that context. Just to remind you, this is the result that's going to give us the applications, and why the application will come about is precisely because of this reason, that in fact we have polynomial sized formulas of small depth for computing the polynomial, for which there are no smaller than little o log d depth formulas computing it. Maybe it's written better on the slide than I said. IMM has small polynomial size formulas of depth order log d, but for any depth less than that, little o of log d, we have super polynomial lower bounds. This is what will give us these applications. So let me start with the first application. This is an application which says that formula depth reduction in the multilinear world is tight. So depth reduction, a small introduction to depth reduction. I think it needs no introduction, but let me just say it anyway. Any polynomial on n variables of degree poly n computable by a formula of size poly n is also computable by size poly n and depth log d formulas. This is a result for formulas by Spira and Brent. Similarly, any polynomial on n variables of degree poly n computable by size s and poly n circuits is also computable by size poly n and log depth circuits. This is a result of Welians, Kuhn, Berkowitz and Rakov. And any polynomial on n variables, so this is a more recent result which
the
squeezes
second
it
one.
down to depth 4. Sorry?
The second result is unbounded fan-in for addition, right?
Yes. Yeah.
What?
So to go to log depth, you require that the AND fan-in is unbounded, otherwise you get depth log square. So this result started by Agrawal, Vinay, Coran and Tavanas. Squeezes it down to depth 4. There is another depth reduction result which squeezes it down to depth 3, but I'll talk about it in another context, so let me not list it here. One natural question would be, are these results tight? In their most generality, of course, this problem is wide open. We don't know. How about for multilinear formulas or multilinear circuits? Are these depth reductions tight in the multilinear world? Okay. So there are results that I already mentioned. Let me go through them slightly quickly. There exists an explicit polynomial on n variables computable by multilinear circuits of poly size and require multilinear formulas of size n to the omega log n. This result of from 2006, 4, 8, etc. Shows depth reduction is tight for multilinear circuits. So this gives tightness for depth reduction for multilinear circuits. In particular, it shows that VSBR, when applied to multilinear circuits, is in fact tight. Okay, so this was known. What we show is tightness of formula depth reduction.
So the reductions are supposed to be preserving multilinearity?
Yeah,
or
that's what I
something?
thought.
So the thing is something that Mrinal talked about, that syntactic multilinearity can also be preserved in a depth reduction. In fact, this result of Raz and Yehudeev from 2008 actually proves that for multilinear circuits, that you can do depth reduction for multilinear circuits while preserving multilinearity.
But
So
the original depth reduction has that property?
original depth reduction requires observations from their paper to notice this property. So in spirit, their depth reduction is very similar to VSBR, but now you have to be a little more careful about ensuring multilinearity. So I don't know, maybe Amir will be able to correct me if I'm saying something wrong.
Yes, the answer is yes.
So that's the status. So they show this. What we show here is that in fact depth reduction for formulas is tight. In particular, to be fully formal, for each d, there exists an explicit polynomial on order d variables such that it has multilinear formulas of polynomial in d size, but any multilinear formula of depth anything smaller, little o of log d, must have size strictly superpolynomial in d. Okay. Well, the hard polynomial is IMMD. It has order d many variables. It is computable by polynomial size circuits of log d depth. And we know that for any depth delta smaller than little o, of the order of little od, it cannot be computed. So it just falls out as a corollary of the result. Nothing going on there.
Sorry, to go back to what you're saying, so this is for unbounded fan-in in...
Yeah.
So, okay.
So because when you start talking about depth bounded, it's just always good to talk about unbounded fan-ins.
But the okay.
So in particular, this shows that the previous depth reduction results are tight in the multilinear world for formulas as well. So that finishes application 1. I'll move over to application 2. Before that, sorry, I'm messing up. So there is something to be said about a subsequent work after 2008 work of Raz and Yehudeev, which was in this paper. it has a close correlation to what I just said. So what they were able to do was they said that they managed to construct a polynomial such that any multilinear product depth little of log n by log n formula computing it must have size n to the omega log n, while it has polynomial size multilinear formula of depth order log n. So this is kind of again in the spirit of what we wanted. Unfortunately, this can be used to give superpolynomial separations between size s and depth little of square root log s by log. So these functions are not important. It's just not it can't be used to prove separation between size s and little o log s. So when you are able to say such a thing, only then can you say that depth reduction is tight, because depth reduction stops at that depth, not at square root s depth. So they almost had this result. So it's not the first time that such a thing has been shown or something, but because we get this tightness that we pointed out that delta in the exponent is kind of crucial. It allows us to salvage the statement that depth reduction is tight. Alright. So I think I'm now truly done with mentioning application 1. Let me talk about application 2. So this is about how strong are formulas, how strong are circuits as compared to formulas. This question can be asked in general, of course. We try to answer it in the multilinear setting. Given any multilinear circuit of size s and product depth delta, there is an equivalent formula of size s to the order delta and product depth delta. This we already saw. The question one can ask is this conversion tight? Can we get formulas of product depth delta but size s to the little o delta? So here is where I'll mention the result Avi was pointing out. So settling such a question in the Boolean world would imply a separation between NC1 and NC2. And such a statement is in fact known. For delta of this order, but for a fixed epsilon, a result of Rossmann and Srinivasan shows that in fact in this regime of delta, the answer to that question is no. You cannot write down, so let me say it appropriately, it's not written on the slides. Any size s circuit of product depth delta, if you were to convert to size product depth delta but size s to the little o of delta, this is not possible as long as delta is in this regime for Boolean circuits. In the arithmetic setting, in fact, such a thing was known by Raz's result, which is famously known as multilinear NC1 not equals to multilinear NC2. Right? But unfortunately, Raz's result cannot work for small delta, where in the arithmetic world that is also interesting. So Raz's result works for delta equal to order log s, but for small delta, we recover this result as well. So again, there was an evidence to the fact that these two should not be equal. We kind of say that they are not equal. So just to put down the formal statement, the following holds for some fixed constant epsilon. Let s and delta be growing parameters with delta being like this. Exactly the parameter settings of Rossmann and Srinivasan and Rossmann. There is an explicit polynomial fs delta that is computed by product depth delta syntactic multilinear circuits of size at most s, but any multilinear formula of product depth at most delta that computes it must have size s to the omega delta. So exactly what we were asking has been answered for small delta as well.
So is that really a gap between this and Raz's result now? I mean, so you get log s or log s over log s, but in between?
Yeah, there's a gray
It's
area.
actually a gap, okay.
Yeah. That may be hard to, I don't know. Yeah, there is.
Is it possible that there is a reduction from just the Boolean lower bound to the multilinear arithmetic lower bound?
That's a good question. We were kind of hoping that something like this holds, but we don't know how to make it work. Most of the proofs, so probably you're asking, is there an inspired polynomial that we can construct from the Boolean example?
The function is the same, it's reachability and so on.
That's true.
It's iterated matrix multiplication in both cases.
That's
Only
true.
Boolean iterated matrix, yeah. So it's not a problem. Just whether, maybe if you had a multilinear one, you can get a Boolean one and this lower bound will fall.
So I have to say we tried this approach. I don't often recall where we got stuck at that point, but we were not able to push this forward. So I don't know. Maybe there is a simpler way to do it, to recover this statement from the known results. So let me now talk about the third application. As always, there is one more slide before I go to the third application. I'm actually trying to give a small proof for this, which is not very, I don't know whether it's going to be more helpful to look at this proof. I have a slide for it, let me kind of go through it right now. There is some parameter setting that one can do, which is careful but not difficult, which can ensure that S that we are dealing with is 2 to the order d to the 1 by delta. Now let the sth polynomial, S delta polynomial, be this IMM d, where d is chosen so. Now this naturally by definition has multilinear circuits of size S for IMM, but any multilinear formula for this must have size S to the omega 1. So all I am trying to say in this slide is that there is a setting of d which can recover this lower bound. So as I said, this slide is not that helpful, so I can maybe move forward. The third application, so I must say that this application was pointed to us by Mrinal, the third application is the question of separating formulas which are multilinear versus general formulas. So given a general formula, product depth delta and size S, that computes a multilinear polynomial P, we can obtain an equivalent multilinear formula of product depth delta and size S to the order 1. So can this be done? So can I always convert a general formula into a multilinear one? This question was posed in the survey of Shpilka and Yehudev, and we give an answer to this, which is, as we are in the lower bound workshop, the answer is no. So here is the exact statement. Unfortunately, this result depends on characteristic zero fields because what I use inside it depends on characteristic zero fields. So the field is of characteristic 0, S be any growing parameter, delta be such that delta is little o of S. There is an explicit multilinear polynomial, say fs delta, such that it has product of delta formula of size S, but any product of delta multilinear formula for this must have growing superpolynomial size. So that is the statement. So what happens is, again the polynomial, it's no surprise that the polynomial is going to be IMM. What we are able to do by a previous result of depth reduction of Gupta, Kamath, Kayal and Saptarshi, we are able to give a better depth, better small depth non-multilinear circuit or non-multilinear formula for IMM. And that's how this separation comes about. Let me say a little more about this. We use the same divide and conquer strategy that I talked about over here. It's exactly the same sort of strategy, except this outer IMM, instead of doing this kind of stupid brute force 2 to the t approach, we say that this IMM could be written by a depth 3 circuit, sigma pi sigma depth 3 circuit that has size n to the square root t. So this is what their upper bound tells us. And now if you just put this into the recursion, you will see that you in fact get circuits of size one by 2 delta instead of 1 by delta. And
This doesn't preserve multilinearity.
this doesn't preserve multilinearity, unfortunately, or
And that's where you save because
that's where we say exactly.
This was observed by Audi and Sebastian.
This separation.
This 2 delta that you have.
Okay. Yes.
Sorry, so they prove that IMM of T matrices and by matrices can be done by depth 3.
So depth 3 circuits of size n to the square root d.
And this is an arbitrary circuit with no partial restriction. It's not multilinear.
Yeah, it turns out to be inhomogeneous, non-multilinear, all sorts of bad things. Yeah.
So if you're doing depth 3, how do you make sure that the overall depth hasn't gone up in that?
Yeah, that's a good point. So over here, for this circuit, for this recursively, I have a sigma pi, such a circuit, sigma pi, and then you have a sigma pi sigma circuit. So these sigmas can kind of collapse. So yeah.
So, so you pointed out that it only works for characteristic 0. So the reason is that because JKKS only works for characteristic 0. That's the bottleneck.
That's the bottleneck. So the point is, as I said, instead of doing the stupid divide and conquer strategy, do this clever strategy where you apply depth reduction at this. Works over characteristic only 0, unfortunately, and we get non-multilinear formulas of, so from the circuits, as I said, as always, we can recover a formula of this size for IMMD. Yes, sir.
Yeah, but I think to be fair to the open question, whether it's in Spilka or Dyer for the general open, it's really interesting for delta equals log S, not little log. That's where Raz's result breaks down.
Breaks down. Yeah. No, I agree.
So the answer no is for the regime that.
Yeah. So I should qualify that we haven't answered the question in its full generality. The question is more interesting, as Avi said, at order log S, depth order log S. So that remains open actually.
and there in fact an answer yes is more interesting, right?
Yes, well,
yeah.
we don't know, but yeah, either answer will be interesting. Raz's lower bound is n to the log m, lower bound for multilinear, and the best upper bound we know, non-multilinear, is n to the log.
So, but yeah, that question is still open. So we answer it in this regime, which is some evidence probably for what we can expect, but yeah, it doesn't settle the question in its full generality. Alright, so again we do some parameter setting. This slide, like before, is not very interesting, I would say. There is believe me that there is a setting of parameters which achieves this. That's all this slide is trying to say. So now I've told you what the result is, what the 3 applications are. In the rest of the time, and I might end early, I'll just tell you the proof outline for the statement, the main theorem statement that I mentioned earlier. So it helps to think about IMM as a graph. This again most of us probably are familiar with. Just setting up some notation, so I'll say it anyway. Let pi be a path. Let graph this graph be denoted by GD because it has D layers, and let lambda pi denote the product of the labels on the edges in pi. So it's easy to see that the IMM version that we defined, which is sum of the first two rows of the product matrix, is simply the product of the path labels summed over both the possibilities of the sinks. This graph theoretic view will somehow help us. And if I open it up, it will tell you exactly what path I take opening up pi, and then we sum over all these things. So we proved this result as most lower bound results are proved in two steps. First, we say that formulas are weak. So there is a structural lemma that exposes the weakness of the formula. And to talk about the weakness of the formula, I'll introduce some notion called as product depth, small product depth. So what we do is the structural statement is going to say that we have a small sum of products of polynomials where each product term has many factors. Yeah, I'll make this clearer in the next slide. This is just the outline. So step 1 is going to give a structural statement about multilinear formulas, and for those who have seen similar statements, this outline may be very familiar. Step 2 is going to say that the decomposition that we could achieve or the weakness that we could expose for the multilinear formulas does not hold for IMM, and that will basically prove the result. So let me tell you what this weakness of multilinear formulas is going to be. As pointed out yesterday, many lower bounds, we are not going to be able to do too much with rank lower bounds, but for some restricted settings, maybe we are still in the business.
So does it apply formally, that barrier that...
Yeah, absolutely. So it's a purely rank-based method, so barriers apply. But barriers are for separating VP, VNP, etc. These are slightly less ambitious things, I think. So let F be, so the structural lemma about multilinear formulas is, let F be a polynomial on n variables computed by a multilinear formula of size S and product depth delta. Then it can be written as follows. F is a sum of S many things, where each thing inside it is a product of polynomials, where the only structural property that these FIs must have is that they should depend on disjoint set of variables. And moreover, each term inside this summation should have lots of factors. Lots of factors. Yeah, and if you see, the number of factors we are talking about has that same expression that we expect in the exponent. What's going to happen is, if I can write a formula like this, then I'm going to be able to kind of put a restriction on my variables, and this restriction is going to give me rank deficiency in these factors. And if there are more factors, I get more rank deficiency. And because rank is subadditive, you can show that overall rank of anything that can be written down in this format is not too much. Again, I'll make this clear in the next few slides, but that's the outline. Yeah, Varun.
There's a similar statement in Raz Yehudev, right?
Yeah.
But is the number of factors, are you getting something?
Yeah, we are getting something better. So I will mention both two things after this.
So this statement is not complete, right?
I will tell you where it is not complete. So the structural lemma I have written down looks very nice and cute and everything, but it is not so in the paper. So if you actually look at the paper, we get this or one ugly case. Okay? The ugly case consists of, you get some simple linear forms there is something more to this statement. So I'm slightly lying over here, but it captures the spirit. So let's just say that this is it.
So is that like arbitrary?
Ram Prasad?
Sorry. So you also need the fact that each Fij is non-trivial.
Yeah. So it has at least one variable in it. Otherwise, you can always do this. You can just put, nothing in all of these. Was that your point, you all also? Yeah. Each of these rests on some number of variables. In fact, in our situation, we just need that they have at least one variable in them. That's going to be enough in our situation.
But are you saying that you need the rank method to prove this lemma, or you use this lemma to prove get the rank?
This lemma will come out by just looking at the formula and observing some structural property. This is in fact a standard depth reduction idea. Depth reduction idea applied fully to get a structure like this. So you can always say that a polynomial f can be written as ax plus b, where a is this recursive substructure you will go deep into, b is another such structure, and now this gives a sigma pi like. So anyway, there is a product lemma like this known from before. So one of them is presented. In fact, so this is in the survey of Shpilka and Yehudeev, which says that if f is a polynomial on n variables that is computed by multilinear formula of size s, then f can be written down like this, where each fi depends on disjoint set of variables, just like in our case, just that they need that the size of each of these is large. They need a size lower bound on it, and they get that the number of factors is only omega log n. Okay. We differ in that sense from this lemma. So this lemma is a reinterpretation of an older result. So what Shpilka Yehudeev have done beautifully in their survey is that many of the previous lower bounds have been presented in a unified way by saying that the class of circuits for which I prove a lower bound, let me write a weakness lemma for them. And all their weakness lemmas look like this. Yeah? In the original papers, they have not been presented like this, not necessarily presented like this, but in their survey, they do this unified thing of writing down the weakness of a model of computation by writing down such a lemma, which is very helpful in my opinion. There is another such statement that Mrinal was talking about, which appears in a paper of Raz and Yehudeev. They also give such a decomposition. They also unfortunately need that every polynomial depends on a large set of variables, and what they get as the number of factors is n to the 1 by 2 delta. So the dependence on delta that is sitting next to this term is not there.
But this is when your polynomial is computed by a depth delta formula.
That's right.
Product depth product depth delta is also there.
Yeah, I should say that. Yeah, that delta is product depth delta. Yeah, sorry. You're right. So this is a statement. So they are very similar in spirit, and in fact in the survey you will find at least 2 more such statements which are quite similar in spirit. So we differ in this way from the previous statements of the similar nature. So now stepping back a little bit, this is how we prove a lower bound. This is again familiar to everybody here probably. Let me just say it. Let's define, so this is the rank based method which I'll just explain now. Mu is a map from polynomials to say reals. You show that your computational model, when mu applied to your computational model, the quantity you recover is quite small, say S times capital S, where S is the size of the formula or the model you are looking at. Then for the polynomial that you are trying to work with, you show that mu applied to that is quite large. And then by just comparison, you can get things like, the size of the circuit better be L by S. So this is a standard outline that we keep on applying. The difficult part usually is coming up with the right polynomial and coming up with the right measure, and also sometimes coming up with the right lemma or weakness of the model. So the measure that we will use, so from now on I probably will end in 5 minutes and not give too many details, just the outline. Design a random restriction. So our measure is going to be a rank of a certain matrix. However, the matrix is obtained by first applying this operation. You do a random map from the set of variables that you have to two sets of variables y, z, and maybe some constants. Distinct elements of x get mapped to y, z, preserving multilinearity. This is something we'll need while working against multilinear circuits or formulas. And now when you get this new polynomial g, which is over these y and z variables, define mu to be the rank of the partial derivative matrix of y comma z. The partial derivative matrix is nothing but you label the rows with y monomials, label the columns with z monomials, and a particular entry in this is the coefficient of the corresponding product of the monomial obtained by taking the row monomial times the column monomial. So this is the measure we are going to apply. Let's see, I haven't even told you what this measure is exactly, but I'll just give you an example of it for IMM, and then we'll kind of understand what the measure should be.
But it's the same one that Van Raas applies to the determinant. This partition of variables.
It is partition of variables. One has to be a little careful. Yeah. So let me just show it to you in an example as to what the measure is. What we do is, for some of the layers, so imagine I have this set of variables, but think of them as appearing in this IMM instance for now. They may be appearing anywhere in the formula that we are trying to beat, but for IMM it appears so. So you have this IMM instance. For some layers, you call them active layers, and some layers you call passive layers. So in the passive layers, either you embed an entry like this in the matrix, or so passive layers don't have variables coming from y or z. They either swap the previous polynomial or propagate it as is. And in the active layers, you have, if the previous active layer was mapped to y, then you map this one to z, but you have maybe two choices for doing that. Either the y could be mapped like this, so you keep these two edges alive, or you keep, maybe it's better with z. Yeah, there are two choices of doing this while keeping one diagonal alive, diagonal and lower edge or diagonal and upper edge. And you keep doing this. Yeah. So without going into too many details, just examining what such a restriction does to this graph, you can see that this IMM 9 under this restriction row yields this polynomial. If you kind of just multiply it out, you see this. If this last factor wasn't there, then you have a 2 cross 2 matrix of the partial derivative matrix of full rank. The x variables, y variables are just degree 1 polynomials, and you have this. And with this, the rank falls a little bit, but usually it will fall by just 1. You will have 1 extra y variable, if at all any. So that's how it will work for IMM. And for IMM, you will recover basically full rank under this restriction. So, yeah.
Building on Avi's question, the difference between this and Raas's thing is that Raas typically considers a random partition.
Random partition.
But you're choosing your partition in a
slightly carefully. Yeah.
But you want full rank. I mean, that's what in the determinant case.
That's right.
That's what you naturally get full rank, and here that's what gives you full rank.
Yeah, but now I guess the task is to argue that under this random partition, the circuit model is.
Yeah, sure, you still do it. Yeah.
One also doesn't choose a random partition.
Yeah, because there also actually on the sub-diagonal, there is a thing. Everywhere else he puts a 0. So there is a very, actually he does these 2 cross 2 matrices and does a, yeah, but there you will recover quite a good rank even by probably, okay, but I don't know. Yeah. Okay, so this is what happens to the polynomial under the chosen restriction. As Avi said, basically choose the restriction that gives you full rank for the polynomial, and then the hard work remains to show that it actually works even in the case of the polynomial, in the case of the formula. So polynomial is computable. So what we prove to show low rank is the following statement. If f is in that product decomposition format, then under the random restriction that I vaguely talked about in the previous slide, the probability that the rank of this partial derivative matrix is large is very small, and the small depends on this t, and that's how we get the lower bound. So once you show rank deficiency for the model and full rank for the polynomial, standard computations will give you a lower bound. So basically that, yeah.
I'm not sure if it's a question or a comment, maybe even not for you, but it's related to what Ketan asked before. I don't see how to implement this in the formalisms Klim spoke about. Here there is the distribution on linear functionals, and for every, once you choose a small set of simple polynomials, then you can argue something with high probability. And I don't know, I don't see, it doesn't fit immediately into the same formalism.
Okay, so I'm happy to know that, because yesterday actually during Klim's talk I was asking him exactly that if I hit it with a random restriction and do some other stuff, does it fit? But I think the answer is yes to that question is what I understood yesterday, but I'm not aware of this, so yeah, we can talk about this, yeah. Maybe this will go into a discussion, so let me just finish my talk and then we can do that. So in summary, we proved this result. It has 3 applications. It shows the tightness of depth reduction. It shows non-trivial separations between small depth multilinear formulas and circuits, and it shows non-trivial separations between non-multilinear and multilinear formulas. So with that. Yeah.
So what about PIT for this multilinear thing? Has it been all solved because of all this? Or?
So read once PIT has been solved by Ilya that he presented yesterday.
And general?
I don't think so.
So these lower bounds don't help in?
Hopefully they will help on some day, but right now we don't have.
So what's the bottleneck?
I'm not an expert on PIT. I'm not sure. Maybe Ilya should answer this.
It's sort of the hope, the goal is that once we have lower bounds, we could do PIT, but there is this, how you take a lower bound and convert it into an algorithm.
Oh, so you need that factor.
So it's like one way to do it is like do like a Cabanets and Pogliazzo, but the point is if you want to do like, even for multilinear, your lower bound has to be non-for multilinear, because this Nissan-Wigderson generator actually makes your polynomial non-multilinear. So this is one of the issues. I actually tried these things before. Okay. So the state of affairs was, even for read-once formula, we couldn't find the strong enough lower bound to do Cabanets and Pogliazzo. This was like very sad.
Oh, so that is the bottleneck.
I'm not sure about what exactly, but
I mean, not every lower bound to PIT actually goes via.
Yeah, so many examples are there where we don't know how to convert lower bounds to
historically
PIT.
it has been that you get a lower bound and then you get a PIT. This has not happened for multilinear formulas yet.
Yes.
Yes, Sam.
Can you go back one slide?
Yeah.
Yeah, I was just hoping you'll tell us one bit of information. So in this old paper, the norm, we get the same lower bound without the delta in the exponent. What do you do to get the extra delta? We of course use a different random restrictions. But
so the thing is, our product lemma is what is saving us.
Yeah, but what in the product lemma gives you this?
What in the product lemma gives us this? So we are able to break the circuit slightly, break the formula in a slightly better way. I can explain it to you on paper later on.
Maybe the previous slide that you had.
Sure.
So here it's important that in your case the m that you have in the m is a random variable.
Yeah.
Like the number of variables that are going to be alive.
Yeah. So that's the other point also in the thing that we don't. Yeah, you're right. Yeah. So the restriction is such that it knocks off lots of variables. Actually, it keeps many layers inactive. But in terms of the live variables, we recover a good separation. That also kind of turns out to be important.
So if you use a decomposition lemma for circuits and apply the same restriction, you'll recover their bound?
Say that again. If I start with...
For the papers of Ben, which give a slightly better result for formula, it's the case that if you use the regular switching lemma polynomial method, you recover the usual bound.
I see. So, in this situation, by that way, I don't know how to recover. Maybe there is a way. So, of course, it recovers the bound because, the conversion between formula and circuits is not that expensive. But maybe it does. I'm not sure.
You just need that decomposition lemma with now this delta factor.
Yeah.
Other questions? Comments? Okay, thanks.